Good morning, Internet. I am Matt Buyak, and in this video, we'll be taking a look at the 16th problem from the Project Euler problem archive. Now, this problem asks us to find the sum of the digits of the number 2 to the 1,000. So let's get into it. Let's start with how we find the digits of any number. The most practical response, perhaps, would be that we just use sprintf, convert it to a string, and then we're done. Great. But that doesn't provide any particular insight into how we might do this with larger numbers, or in particular with our number 2 to the 1,000th. So we have to get a little bit back to basics here. Okay, so let's, as usual, copy our template directory to make our problem directory and open our analysis file. All right, so let's start with a simpler number. Let's just say, n equals 1, 2, 3, 4, 5. And we want to ask the question of how we extract the digits from this number. And so we might observe that we can write, 12,345 is equal to 1, 2, 3, 4 times 10 plus 5. That is 12,345 divided by 10 is 1, 2, 3, 4, remainder 5. And so in this way, we can extract the least significant digit from this number. Now, recall in C and C++, the remainder is calculated with the modulus operator, and that's this here. Okay, so that means that we can just do 1, 2, 3, 4, 5 mod 10 gives us the first digit 5. Now, how do we get the next digit, this 4 here? Well, we need some way of getting 1,234 from our starting number here, and so you might think that we can just do 1,234, 12,345 divided by 10 is equal to 1,234.5. And so then if we just take the floor of that, that's going to give us our result. But it turns out we don't have to involve the floor function at all, and that's because with integer division in C and C++, this is already true with integer division. So we don't have to explicitly take the floor function. Let's see. So this kind of suggests how we can go about extracting all the rest of the digits for this number. Continuing the process, we'll just do 1, 2, 3, 4, 5 mod 10 is equal to 5. And then 1, 2, 3, 4, 5 divided by 10 mod 10 is equal to 4. And then we have, divided by 100 mod 10 is equal to 3. Divided by 1,000 mod 10 is equal to 2. Divided by 10,000 mod 10 is equal to 1. and eventually we get to divided by 100,000 mod 10 is equal to 0, and that's how we know to stop. Okay, so this shows us how we can extract the digits of this number from this number. And so if, suppose, this were the number that we were asked about in our problem, we would then just sum the digits and have our answer. And in fact, we have enough at this point that we can solve their example input here, 2 to the 15th, and finding the sum of those digits. So just as a useful starting place, let's do that. So let's jump over to our main.cpp. Okay, so let's see. We're going to want to say uint32t, n is equal to 1 shift left 15. Note that this is just 2 to the 15th, which was the number that we're given here. And then we want to say, while n is not equal to 0, let's see, we're going to need some, we want the remainder. And so we'll say, oh, and we'll also want our sum. Okay, so now we can say, remainder is equal to n mod 10. So this is just what I was describing in our analysis. And then we want to say n divided by 10 is the new value of n. And then we can just say sum is equal to sum plus remainder. And then down here we'll say printf sum is equal to sum. Okay, gives us our digits summing to 26. That does match the output. Out of curiosity, we can say uint32t. Actually, we can just write here, say printf digit equals remainder. Okay, and we can see there 32768, matching our number here, 32768. Okay, great. Now it might seem like we're most of the way there. That all we got to do is go up here, crank this up to 1,000, change this to a uint 1024t or whatever, and then we're done. The problem is that this data type doesn't exist, and this won't do what you think it does. This actually is valid syntax, but it won't do what you think it does. And so we need some way of working with larger numbers. The largest numbers that that we can represent using these 32-bit integers is 2 to the 32nd minus 1, which is roughly 4 billion. And so that's not going to cut it for our purposes. All right, so back to our analysis. We need a way of representing larger numbers. So let's get back to basics. How do we represent numbers? This may seem like a stupid question, but like, what does this actually mean anyway? when we say, 12,345 represented in this way, what we're really saying is, 1 times 10,000 plus 2 times 1,000 plus 3 times 100 plus 4 times 10 plus 5. And for reasons that may become clear shortly, I'm going to rewrite this as 10 to the 4th, 10 to the 3rd, 10 to the 2nd, 10 to the 1st, and 10 to the 0. Okay, so this is what we really mean. This is our decimal number system. When we're representing a number like this, this is what we really mean. But there's no reason we have to be limited to base 10. If I go through here and I swap out 10 for some value b, this would be just as valid in some other number system. B could be 7 or 279. It could be anything, and this would be a valid number system. For any value greater than 1, I might add. You can't actually have a number system, at least in this form, with b equals 1. That doesn't work. Let's see, in particular, if b equals 2, we call that binary. And this is like the language that computers speak. Everything is, about binary, represented as, ones and zeros. So just to give an example of what we might mean by that, if we have, suppose we have a binary number, you'll note that in decimal, which is base 10, we have all the digits are in the range 0 through 9, 9 being the largest number less than our base. And so in binary numbers, we're going to have 0 through 1, just 0 and 1, because 1 is the largest number less than our base of 2. So a binary number might be something like, oops, you don't want to throw a 2 in there. That would not be valid. Suppose we have this binary number here, like that. Okay, so what is the value of that? Well, going back to our representation here, we would write this as 2 to the 8th. Excuse me, I think that's the 7th. So 0, 1, 2, 3, 4, 5, 6, 7. Yes, okay. 2 to the 7th plus 2 to the 4th plus 2 squared plus 2 to the 0. And we can pull up our calculator if we're so inclined, and do 2 to the 7th plus 2 to the 4th plus 2 squared plus 2 to the 0 is just 1. So that's 149. So this is just an example of a binary number. And so, base 2 and base 10 are two very common bases. Another possibility is base 16. And we call that hexadecimal. Or just hex for short. Okay, so why base 16? That seems kind of arbitrary. And the reason that we like base 16, why do we like base 16? Well, the first is that we can easily convert from binary. So to go back to our example from up here, if we have this binary number and we group this into groups of 4 bits here, then that's just going to be 95 in hex. And the way I did that was just to look at this first group of 4. That's 9 in binary, and so we have a 9 here. And we look at the second group of 4. That's 5, and so we have a 5 here. And so it's very easy to convert between binary and hex. Much easier than, say, between binary and decimal. We had to go through this process of writing this out and calculating each of these values and summing them up, and there was a lot of math involved. And so doing this conversion is much simpler. And the second reason we like base 16 is it's much more compact than binary. So there's no reason we couldn't just use binary as it is, but it tends to be very verbose. Even a small number, 149, was 8 digits. And so hexadecimal is much more efficient in that sense. I would just note that it's actually not the most efficient. 16 is 2 to the 4th, but there's no reason that we couldn't go farther. 2 to the 5th, 2 to the 6th, maybe 2 to the 32nd, all have these same properties that we can easily convert from binary, and that they're much more compact. And in fact, the larger the base, the more compact and efficient our solution is going to be. But for now, because I think it makes it a little bit easier to understand, we're going to stick with base 16. Okay, so I mentioned that it's easy to convert from binary into hex. Let me just make a note here. This is binary. What about 2 to the 1000th? Can we represent that in hexadecimal? And so, first note, in binary, 2 to the 1000 is just a 1 followed by 1000 zeros. And so using our approach for converting from binary to hex, we can just say in hex, therefore, 2 to the 1000 is just a 1 followed by 250 zeros. Okay, so now we have our representation of our number 2 to the 1000th. Now we just need to be able to do division and take remainders when dividing by 10. But before I move on to that, there's one wrinkle of hexadecimal notation that I haven't mentioned that I feel like I probably should. Otherwise, I'm sure you'll be asking this question the entire time. And that is, how do we represent digits larger than 9 in hex? We don't actually need to know this in order to solve this problem. I'm just putting this in there here so that going forward you have some familiarity with hexadecimal and you'll have the answer to this question. So in particular, we represent 10 as the letter A, 11 as the letter B, 12 as C, 13 as D, 14 as E, and 15 as F. Okay, so with that out of the way, on to division. How do we perform division on our big number here, 2 to the 1,000th? Well, again, it's probably easier to start with a more familiar example and then generalize that to our problem case. So let's see. Let's go back to grade school. And suppose we were given the problem, we want to divide, 1, 2, 3, 4, 5 by 7. So we've got our number here. We're dividing it by 7. Some of you may remember this, some of you may not. Some of you may have learned slightly different techniques for doing division. But the technique that we're going to use is divide, multiply, subtract, bring down. And this is just the classic long division. So let me explain what I mean by this. So first we're going to find the smallest string of digits at the beginning here that's divisible by 7. Not exactly divisible, but it's just greater than 7. So for example, 1 is not greater than 7, but 12 is. And so we'll start with the first step here, divide. So we're going to divide 12 by 7 and get 1. And then we need to find the remainder. And that's where the next two steps come in, multiply and, not subtrace, subtract. So we're going to multiply 1 by 7 and get 7, and subtract to get a remainder of 5. Okay, then for the last step, bring down, we're going to take this 3, bring it down here, and get a new number to divide. And we can continue this process, dividing 53 by 7, multiplying to get 49, subtracting to get 4, bringing down 4, dividing to get 6, multiplying to get 42, subtracting to get 2, bringing down the 5, dividing once again, multiplying to get 21, and subtracting to get a final remainder of 4, and a quotient of 1,763. So that's just the classic long division from grade school that you probably learned, or some variant like that. And so this is roughly the technique that we're going to use to solve our problem. The only difference is that the base is going to be 16 rather than 10. One caveat is that sometimes it can be difficult to determine the number of digits that to use for your starting division. But if we have only a single digit that we're dividing by here, like if the number is whatever 217 or whatever, it gets a little bit more complicated. But if we have just a single digit, then we can add a 0 out in front here, and then we'll always be looking at 2 digits at a time. So you'll note that this doesn't have any effect on our final result. We're just going to get a 0 there and bring down the 1 there, and then everything excuse me, that should be a 0. That's a 1. Bring down the yes, that should be a 0. Remainder 1. Bring down the 2. Yes, there we go. And then everything should work out as before. We need a 7 there. Okay. And so yeah, you'll see that appending this 0 on the front has no effect on our result. But it means that we can always look at 2 digits at a time. Now you may be thinking to yourself, but 10 is it has 2 digits, and so this won't work. But you're forgetting that we're working in base 16, and in base 16, 10 is just a single digit, which is represented as the letter A, and so this approach will work. Okay, so now we have our representation of our number 2 to the 1,000th. We have our approach for how we're going to do the division. Now we can write some code. All right, let's go back over to our main.cpp. And we'll need to store our number. As we recall, we said that 2 to the 1,000th in hex is just going to be a 1 followed by 250 zeros. And so we'll need, we'll call it cells, and we'll have num cells is going to be 251, because that starting 0 followed by 200 starting 1 followed by 250 zeros. Okay, and then we just need to initialize our number so that we have cells num cells minus 1. So that is the very most significant hexadecimal digit is going to be just a 1. Okay. So now we can't easily check to see if this is 0 or not. You'll recall that this is the condition for our while loop here, is whether our number is 0 or not. So let's just say we have this Boolean value 0 that we're going to use to track whether this is 0. We know that it's false to start, and then we'll say while not 0, and then down here we'll say remember to calculate 0. Okay, so now we need to have our division here. So this part, sum plus equals remainder is going to remain the same. We don't need to print out our digits there. So let's see, do division here. Okay. Our remainder does not need to be a 32-bit integer. We're using 8-bit integers to store our values instead. And then we'll also want a variable to store our bring down value. That is the next value from the that we're getting from cells here when we're doing the division. Okay, so as with our example here, we want the remainder initially to be 0. That corresponds to appending this 0 at the beginning. And so we're going to say remainder equals 0. And then we're going to proceed over each pair of digits until we get our final remainder and the result of our division. And so let's, I'm going to make a sort of temporary variable called accumulator, and that's just going to be, that's going to correspond to this pair of digits, or this pair of digits here, after we've combined the the previous remainder with the bring down value here. And we'll also need an index here. And so we'll say for I is equal to num cells minus 1, and we'll say I is greater than or equal to 0 minus minus I. Keep in mind that the way that I'm indexing this, the first digit here has index 0, and then index 1, 2, 3, 4, etc. So that's why we're starting with I equals the last digit at num cells minus 1, and we're decreasing until we get down to the least significant digit. Okay. So first we want to say, bring down is equal to cells I. Okay, and then we're going to say accumulator is equal to 16 times remainder plus bring down. You'll recall from our example here that when we want to combine the remainder, say this 5 with the value that we're bringing down, the 3, we need to multiply the remainder by the base and then add the bring down value. So that's just what we're doing here. And I'm going to make a small optimization. Anytime you're multiplying or dividing by a power of 2, you can just do that using the shift operator. So we'll say, so multiplying by 16 is just the same as shift left 4. Okay, so now we've constructed this value here. We need to do our division and find our remainder. And so we'll say cells I is equal to accumulator divided by 10. So that's the result of our division. And then we'll say remainder is equal to accumulator mod 10. So that's just the modulus operator that I talked about, back at the beginning of our analysis here, as being the way of taking the remainder in C and C++. Okay, so we've updated our value in cells. We've determined our new remainder. So that should be the end of that loop. And so at the end of this loop, the final remainder here will be the digit of our number in base 10, since we've been dividing by 10. Okay, now we have our note here saying remember to calculate 0. And the way we'll do that is just if any of our values in cells are non-zero, then our number is non-zero. And so we want to start with 0 equals true, and then if any value is non-zero, we'll set it to false. And the way we'll do that is just by saying 0 is equal to bring down And so if bring down is non-zero, then we want to set 0 to false. And so we'll say false. Otherwise, we want 0 to be unchanged. So if, in case you don't recall, this is just the ternary operator, which is, has a condition and then a question mark, and then the value that we want if the condition is true, and then the value that we want if the condition is false. Okay, so at the end of this now, 0 should be updated correctly. So we can get rid of that there. And now this should be our sum. So if we go back over to our terminal, we appear to have made some mistakes. Oh, I see. I have not made, this needs to be constant, otherwise it will not be allowed. Okay, so it gives us the result 1,366. So if we go back over to the archive here and pull up the result, you'll see that the answer is indeed 1,366. And so that concludes this video. In the next video, I expect we'll be continuing with problem number 17.